Hello students, welcome to the electrical engineering channel. In this lecture, I will discuss speed of a DC motor, and we know that back EMF in a DC motor EB is equal to V minus IARA, and back EMF is equal to N phi Z over 60 into P over A, so that will be equal to V minus IARA. From this expression, we can evaluate the speed in RPM. So N will be equal to V minus IARA divided by phi multiplied by 60A divided by ZP. So this is the speed in RPM. And in this expression, N is equal to K times EB divided by phi. So EB here is equal to V minus IARA. And this is phi, right? EB over phi, and this is constant. The number of parallel paths in a DC motor are constant when a machine has been completely designed. Similarly, number of conductors and number of poles, they cannot change once a motor is designed. For a running motor, we can only change the back EMF and the magnetic flux. So from this expression, the speed is directly proportional to the back EMF and its speed is inversely proportional to the magnetic flux. So speed regulation can be defined as the relative difference of no load speed and full load speed with respect to the full load speed. So mathematically, it is equal to no load speed minus full load speed divided by full load speed multiplied by 100, and that will be equal to delta n by n multiplied by 100. So percentage speed regulation in DC motors is same as the voltage regulation in transformers. So N is equal to K times V minus IARA divided by phi, and that can be written as K times EV divided by phi. K is constant. So this is the expression for the speed. Similarly, the torque is directly proportional to magnetic flux multiplied by the armature current. Now we will draw motor characteristics based on these expressions of speed and torque. One characteristic of the motor is between torque and armature current. Another characteristic is between speed and armature current. And these two characteristics are called electrical characteristics. Right? So between T and IA and N and IA. The third characteristic is between speed and torque. And in the third characteristic, we can see that both the terms are mechanical. Speed and torque are the mechanical terms. Voltage and current are the electrical terms. And in these two characteristics, we can observe armature current. So that's why these characteristics are called electrical characteristics. And in this characteristic, both the terms are mechanical. So these are called mechanical characteristics. And we will remember these two expressions of torque and speed before drawing these characteristics of DC motors. So let's first discuss series motor. And in series motor, first characteristic is between torque and armature current. We know that in series motors, when we increase the armature current, so it means we are also increasing the field current, because in series motors, field winding and armature windings are connected in series and same current flows through the armature and the field windings. So IA is equal to IF, and we know that T is proportional to flux multiplied by IA, and flux is proportional to field current IF, and IF is equal to IA. So torque is proportional to IA square. So that's why we are getting a parabolic curve of the torque in series motors, right? Because torque is equal proportional to IA square. So that's why this is a parabolic curve. Similarly, the speed is directly proportional to the back EMF and it is inversely proportional to the flux. And if we draw a curve between speed and armature current, it will be somewhat like this, because armature current is equal to field current, and here the flux is proportional to the field current. So we can write field current over here, and field current is equal to armature current. So it is N proportional to EB divided by IA. So N is inversely proportional to IA. So we will get an inverse relationship between the series motor speed and the armature current. Now the last characteristic is the mechanical characteristic between speed and torque. And we can observe that the torque is almost directly proportional to the square of the armature current. So if we increase the armature current, we are increasing the torque. So while drawing the characteristic between speed and torque is at the x-axis, that curve will be somewhat like the curve between speed and armature current, because torque and armature current are directly proportional to each other. So even if it is armature current or it is a torque, we will have an inverse relationship between the speed and torque for a DC series motor. Now I will discuss the characteristic of DC shunt motor. And in DC shunt motor, the field winding and armature windings are connected in parallel, and field winding is separate and armature winding is separate, and different currents are actually flowing through these two windings. So armature current doesn't depend on field current, and in that case, if we are going to plot a curve between torque and Ia, that will be a straight line because torque is proportional to Ia. So we will get a straight line over here, and that is actually the armature torque. Now, one thing that I want to highlight is that in DC motors, one is armature torque, which is developed in the armature winding, and another is a shaft torque, which is available at the output shaft. Clearly, shaft torque is smaller than the armature torque due to the presence of mechanical losses, right? So, armature torque is developed in the armature, and shaft torque is available at the output shaft, and shaft torque is obtained by subtracting mechanical losses, which are windage losses, friction losses, bearing losses from the armature torque. So if we subtract these mechanical losses from the armature torque, we will get the shaft torque. So that will be smaller as compared to the armature torque. So here again, shaft torque will be smaller than the armature torque, but that will also be a straight line. Similarly, here the shape of the shaft torque is the same as the armature torque, but it will be smaller than the armature torque. So here it will be a straight line. Now the curve between speed and Ia will be somewhat like this, right? If we increase the armature current, then V minus IaRa will decrease, so speed will also decrease. So this is the curve which is available between the speed and the armature current. So over a wide range of armature current, the speed of DC shunt motor is almost a flat line, right? So it is decreasing with increasing armature current, but it is decreasing at a smaller rate, right? Similarly, since armature current and torque are directly proportional to each other, so same curve will be obtained between speed and torque, because either we increase Ia, we are increasing the torque. So the curve between N and T will be the same as the curve between N and Ia, because I and T are directly proportional to each other. So from these curves, we can observe that series motors are variable speed with high T start machines, right? So series motors are actually variable speed motors. So their speed is very much variable. But since in series motors, torque is proportional to Ia square, so the starting torque of series motors is high compared to the shunt motors. But they are variable speed motors, right? So starting torque is high, but they are variable speed motors and they are suitable for traction work, trolley cars, cranes, and conveyors. Uh, Paradoxically, shunt motors are constant speed motors. You can see that the speed profile is almost constant over a wide range of the armature current, but their starting torque is medium because in shunt motors, T is proportional to Ia. In series motors, T is proportional to Ia square. So that's why in shunt motors, we achieve a constant speed, but starting torque is medium, and they are suitable for lathe machines, blowers, fans, and machine tools. So that is all about our today's lecture, and in this lecture, we discussed the electrical and mechanical characteristics of DC shunt motors and DC series motors and their properties. For watching more lectures, please subscribe this channel. Until the next lecture, it's goodbye.